Okay, guys, we're going to start with our Chapter 10 lessons. This is a review that you need before starting Chapter 10. Chapter 10 is all about fraction exponents and radicals. And there's a connection between fraction exponents and radicals, which we will learn in 10.2. But in order for us to handle fraction exponents, we need to remember how to handle whole number exponents. So that's why I put together this review for you. These are documents that are scanned and posted to your Blackboard under content. I highly suggest that you open those documents and have them out while we're going over this. I can't really adjust the focus on this webcam, so it makes the font in printed documents hard to see. You can see my handwriting pretty well, but it's going to help if you have yours nearby so that you can see things a little bit more clearly when it comes to print. Alright, so I also recommend that you pause the video whenever you need to if you feel like I'm going too fast, or if you need to jot down a question, because we will have Q&A sessions on Blackboard Collaborate Ultra next week. So in order for you to kind of remember where you had questions, you might need to pause for a moment and jot that down. Okay, so we're going to get started. Like I said, most of the time you won't have an issue seeing because I'll be writing. But for these documents, you're going to need to look on your paper or your computer screen. If you're splitting your screen, you can probably open up some of these and have them on the same screen of your computer. Okay, so a lot of this you learned in 703, if you had that here, but some of you it's been a while. So we need to remember what to do with exponents in general. In order to do things with exponents, you have to have the same base. So you can see in this first example, x to the m times x to the n. So I'm allowed to add those exponents because they have the same base. I added some parentheses here because I want you to understand that a big indicator for adding exponents is when all of your exponents are inside of parentheses. It's like a visual thing. If there's no exponents hanging out on the outside of the parenthesis, I know that I'm supposed to add them. So it helps me sometimes to point that out. This is a 9 and a 6, so 9 plus 6 is 15. There are some other examples underneath there that you can look at. See if you get the same answer as they did. Numbers can also be bases. So I showed you an example like that. But in Chapter 10, the majority of the time, you'll be dealing with fraction exponents, like I said. So same base. I know I add these, but they're fractions, so I need a common denominator. Walked you through that here. The answer is x to the 11 over 15 power. If you still struggle and make mistakes with getting a common denominator, remember I showed you some tricks on the calculator to do to keep you from making those mistakes. And I can review those during Q&A, again, for anybody that needs them. But yeah, you're going to have to be adding fraction exponents sometimes in Chapter 10. So that's an example for you. You also need to know how to subtract exponents. Whenever you have a quotient or a fraction, I know that I can subtract the exponents. There are two different ways to do this, but one of the ways involves knowing how to handle negative exponents. So I'm going to hold off on this particular method. Most people do problems like this by looking at where the majority of an exponent or for a variable is. I have m's and n's in this problem. When I look at the m's, there are more m's on bottom originally. That tells me that when I subtract those numbers, I need to put my answer on the bottom. Three minus 9 If you do it top minus bottom, you do get a negative 6. But I'm going to talk about that later. Hopefully you understand that if I had 3 m's on top and 9 m's on bottom, I could cancel some of those, and it would leave 6 on the bottom. So that's a positive 6 on the bottom. I'll talk about the negative part later. With our n's, 5 minus 3 is 2. And there are more n's in the numerator, so I put that n squared on the top. Guys, your coefficients are handled normally. You know, this is the fraction 6 over negative 18. So I know I can reduce that. 6 divided by 6 divided by 6 is 1, and 18 divided by 6 is 3. So we handle whole number coefficients regularly and reduce them like regular fractions. If you want to have the 1 in your answer, you can. But it's imaginary, you don't necessarily have to have it. Okay? So I hope you understand this whole objective of canceling and putting the remaining variables wherever the larger exponent is. Look through some of these examples and make sure you understand. Okay? I'm going to come back to this after I talk about negative exponents again. So the power rule is when you have exponents outside of parentheses. So you can see this is the exponent on the outside. If they're on the outside, you have to multiply with them. I want to look at this example. There's a 4 outside the parentheses, so I know I need to multiply it. That's how they got m to the 20th power. But I even have to apply it to the coefficient. But I have to apply it to the exponent for the coefficient. There's an imaginary 1 there, negative 2 to the first power. So 1 times 4 is 4. So really I have negative 2 to the 4th power now. And negative 2 to the 4th power is 16. So you have to apply these exponents that are on the outside of parentheses to the coefficient also. It's the biggest mistake I see. You can see another example down here. Same thing. This 3 had to be distributed to the coefficient as well. Negative 3 to the 3rd power is negative 27. But you will also be dealing with fraction exponents in this way in Chapter 10. If I am multiplying fractions, I do not need a common denominator. I multiply straight across. Make sure you remember that. Okay? I did not show a fraction example with your quotient property because you're not going to have to subtract fractions as much in Chapter 10. But you will still have to deal with this a little bit. So you'll see why I included it a little bit later. Only a few times will you have to subtract fractions. If you have to subtract fraction exponents, guys, you still need a common denominator, right? It's just you don't see it a whole lot. So what's up with this negative exponent thing? All right, well, let's turn this over. There's a reason why I have the squiggly blue lines. This is the primary rule you need to review for Chapter 10. You don't do a lot of zero property in Chapter 10, so you can kind of ignore that, but it is there for you. There is a zero property rule. You're going to primarily need the negative exponent rule. This first example is really complicated. You won't do this necessarily in Chapter 10, but you might see something like this. Okay, so I'm going to primarily talk about this example. So a negative exponent has to be changed. It's considered not simplified all the way if you have a negative exponent in a problem. In order to make that negative exponent positive, you have to move the base with it. Whatever the base is, you move the base and the exponent up or down to change that exponent into a positive number. So if it starts out on top or like a whole number and I need it to be positive, I have to move it to the denominator of a fraction. Then I can change that 1 that was negative. Once I move it down into the denominator, I can make it a positive 1. If it's already in the denominator and it's negative, I need to move it, but I have to move it up. So once I move it with its base up, it becomes positive. It is the up or down movement that changes an exponent from negative to positive. So if we go back to this subtraction rule here, it's always top minus bottom. So when I did my m's, you can also look at this as 3 minus 9 is negative 6. But I would not want m to the negative 6 on top. So it moves down to become positive. I don't have to do that with 5 minus 3 because 5 minus 3 was 2. So it can stay in the numerator. Okay? You don't have to do problems like this, top minus bottom, and move, because a lot of you can tell where the majority of a variable is. But this is a connection to the negative exponent rule. Okay? So, here's a problem with a negative exponent. It was all on top, so I put a little imaginary 1 under there. Because I know with negative exponents, I'm going to have to move some things down. The first thing I want to do, though, is distribute that negative 3 into the parentheses. So we know to multiply whenever the exponent's on the outside. I have to take it to the coefficient. So I'm going to have negative 7 to the negative 3 power. X to the negative 3 power, 8 times negative 3, negative 24, negative 2 times negative 3 is 6. Once I take the negative exponent in, I've got a lot more negative exponents now. Z is the only variable that has a positive exponent, so it's going to get to stay on top. This negative in the front is like having a negative 1 times everything, so it's going to stay there. Negative 1 times 7 to the negative 3 power. Okay, so negative 1 times. It's the 7 to the negative 3 that has to be moved, not the negative in the front, not the negative 1. So 7 to the third is on bottom, but it's positive because I moved it down. X to the negative 3 moves down so that it can become positive. Y to the negative 24 moves down so that it can become positive. Okay? 7 to the third power is 343. Any questions about, oh, see, used to being in the classroom. All right, so ask questions about this in the Q&A if it is still confusing to you. I want to show one more. One interesting thing about a fraction 2x over 4 raised to a negative exponent, you can actually think of this 2 different ways. So in this green way, I distributed the negative 3 into the top and the bottom. But when you distribute a negative exponent in there, they give you a whole bunch of more negatives. Well, all these would have to be moved to become positive. So, you know, I put the negative 3 in here, but these 2 have negative exponents now, so they need to move down to the bottom. And 4 has a negative exponent, which needs to be moved to the top. So that kind of proves that the numerator and the denominator switch places here. So another way of thinking about this, anytime you have a fraction raised to a negative exponent, You can change the exponent positive as long as you flip the fraction inside first. So I flip this, and then you can see that you get the same answer. This would be your answer, 4 to the third. And I would still have to take this 3 in to the 2x as well. 2 to the third is 8, and x to the third. So that's kind of an interesting thing about a fraction when it's raised to a negative exponent. Some people do decide to flip the fraction to take care of that negative exponent. Other people go ahead and multiply the negative exponent in and then move everything negative. So it's really up to you. Okay? Like I said, these have problems on here for you to do. This is a review of the rules. But I also posted for you some extra practice problems just to help you review exponent rules where the exponents are whole numbers and not fractions. I gave you a blank one, and then I saved another one where I showed where some of them were worked out for you. So I showed some more steps here. So I encourage you to look at these problems, at least the ones that were circled, and look over my extra steps to help you and see if you're kind of on track with exponent rules. If you do any more of these, all the answers are down here at the bottom as well. I also gave you a sheet with negative exponents to review, and I showed some more work here. This is attached in Blackboard, so, and answers are here too. So this is extra review with just whole number exponents for those of you that just really need to brush up on these rules before you start doing them with fractions. Okay. So I want to go into 10.1 a little bit before we end this video. So this is the end of the exponent review portion of the video. Okay, all right, in 10.1, they actually review with you radicals. Like I said before, there's a connection between radicals and fraction exponents. So that's why we're having to review whole number exponents, so we know what to do with them when they're fractions. And then you're also going to learn how to convert them into radicals. Okay, so 10.1 just goes into just a review of the radical part before you get to 10.2, which will have fraction exponents. Okay, so 10.1 has square roots, cube roots. They might even have some fourth and fifth roots. You are probably most familiar with square roots. Square root of 36 is 6. Square root of 64 is 8. I showed a little connection here to 10.2. The square root of 36 is actually the same as 36 to the 1/2 power. That's what you're going to learn in 10.2. But you do need to know how to handle radicals. So I showed you some examples here. Chapter 10, sometimes it's fraction exponents and sometimes it's radicals. So you need to know both, whichever form it's in. So if I gave you the problem negative square root of 64, you're going to use your radical knowledge, your square root knowledge, because you know the square root of 64 is 8. When the negative is on the outside, it's -1 times that. So that's okay. But when the negative is on the inside, it's undefined, just for square roots. You could have a problem on the test that way. Negative under the radical as a square root. It's automatically no solution. So if I had square root of negative anything, since that negative is under the radical, it's undefined automatically. Okay, that's something you need to remember. You can do exponents with square roots. okay? As long as you divide by 2. If it's a square root, I'm going to divide by 2. Any exponent. 6 divided by 2 is 3. If it divides evenly, you don't have an exponent in your answer anymore. So the next example, 4 divided by 2 is even, 6 divided by 2 was even, and I know that the square root of 25 is 5. So that's why there's no radical left in my answer, because 25 is a perfect square and all of my exponents divided evenly. Make sure you don't divide 25 by 2. It's not an exponent. Okay? So I showed you some examples here. But sometimes it's not a perfect square number. 48 is not a perfect square. If it's not a perfect square and you're dealing with the square root, you're going to have to do a factor tree. You can start your factor tree any way you want. I started with 12 times 4. You could have started with 2 times 24 or 8 times 6. No matter how you start it, you're going to keep breaking things down until you have all prime numbers. 12 is 4 times 3. So I keep breaking things down. No matter what you started with, you should end up with 1, 2, 3, 4 2s and a 3 when you break down 48. If you're dealing with the square root like we are here, I'm looking for groups of 2. We know the square root of 4 is 2, right? This is a group of 2s. Every group is to come out once. Square root of 4 is 2. Square root of 4 is 2. The 3 doesn't have a pair, so it stays under the radical. Not a perfect square, so I still have a radical in my answer. Here, 11 divided by 2 is not even, so I know I'm going to have a radical in my answer. But 2 does go into 11 5 times. 1, 2, 3, 4, 5 pairs of 2. So that's why I can write x to the 5th on the outside. Okay. All right, so there's 1 left over. That 1 left over has to stay inside the radical. Once again, if it does not divide evenly, you're still going to have a radical in your answer. Okay? The same thing happens for cube roots. I'm still going to treat this the same way. I'm going to have to do factor trees sometimes. I'm going to have to divide by 3 now with my exponents. Okay, so the reason why the cube root of 27 is 3 is because I know 27 is 3 times 3 times 3. And if when a cube root, you need a group of 3 in order to be perfect. 27 is a perfect cube number, so there's no radical left in my answer. 8 is also a perfect cube, 2 times 2 times 2. You can take the cube root of a negative. Okay, it's only even roots where you can't take an even root of a negative number, but an odd is fine. Okay? This is a connection to 10.2. Because remember, we do radicals and fraction exponents in this chapter. So I just wanted to make sure you understood that, or you kind of made a connection that the cube root of 27 is the same thing as 27 to the 1/3 power. If you put 27 to the 1/3 power in your calculator, you'll get 3. But we'll talk more about that in 10.2, the connection between radicals and fraction exponents. This is just how to break down the radical, right? Radical form. This is radical work. You'll see this connection in 10.2. So I divide by 3 instead of 2 because it's a cube root. But since it divides evenly, there's no radical left in my answer. 12 divided by 3 is 4. Here, same thing. It divides evenly. 6 divided by 3 is 2. 15 divided by 3 is 5. So there's no radical left in my answer. Cube root of 125 is 5. There is a way for your calculator to do cube roots. It's usually like a second or a shift key. But 5 times 5 is 25 times 5 is 125. So it's not going to be 125 divided by 3. Only exponents get divided. If you have a fraction, you can break it up and do the numerator first and the denominator separately. Okay, but with the same rule, I'm still dividing by 3. Imperfect cubes still have to have a factor tree, but now it's a cube root. So that means you need a group of 3 of the same number in order to come out of the radical. You still start your factor tree the same way. Think of something that multiplies to give you 72. I did 9 times 8. 12 and 6. There's more. So you can start it any way you want. I did 9 times 8. And I keep breaking it down. 9 is 3 times 3, and 8 is 2 times 4, and just keep on breaking that down. But I know that I need 3 in a group to come outside the radical, so I have 3 2's. So I take a 2 out of the radical. Also because the cube root of 8 is 2, right? There's 2 3's though. They don't have a third 3. So these 2 3's have to stay inside. But 3 times 3 is 9. So that's why I wrote 9 under the radical. 2 3's stay on the inside. $72 is not a perfect cube, so that's why I still had a radical in my answer, but I need to make sure I always put what kind of radical. It's understood to be a square root if there's no number there, but if there is a number there, it needs to be in your answer too. This is a cube root, so I need to make sure I write that. I showed you a imperfect exponent problem. 20 divided by 3 is 6, with 2/3 left over. So I can write x to the 6 on the outside. But there's 2 left over. So x squared, there's 2 x's left over under a cube root. So this is my final answer. It was not perfect, so it still has a cube root in the answer. Okay? To end this video, I want to point out that I posted some practice problems for 10-1. It was a warm-up. So it looks like this. I gave you a blank sheet, and then I gave you an answer sheet. My answer sheet had an extra problem on it that actually went with 10-2, but I thought it was good, so I left it there. Please try to do these. See if you get the same answers. This is a good place for Q&A, so if you have any questions on these, you can bring them up in our Q&A sessions next week. Okay? But this is your warm-up for 10-1. Alright, so I'm going to actually leave the 10-2 intro for the next video and conclude this one. So this is just your review of exponents in general and your 10.1 instruction. Okay? And I'll be with you again here in a minute for 10.2.